Welcome for this second session of the second module. Let us discuss this problems on the Brayton cycle or the gas turbine cycle. See, first problem. Here enters the compressor of an ideal air standard Brayton cycle. Directly he has given the Brayton cycle here. No need to worry. Directly he has given so that the Brayton cycle you are very clear. It is a Brayton cycle at 100 kPa. 100 kPa is pressure. 300 Kelvin with a volumetric flow rate is 6 meter cube per second. Compressor pressure ratio is 10. Turbine inlet temperature is 1500 degree Kelvin. Determine the thermal efficiency, work ratio, power developed. Power developed. Okay. One thing. First,
ಸರ್ ವಾಯ್ಸ್ ಕೇಳಿಸ್ತಿಲ್ಲ ಸರ್.
ಏನ್ ಹೇಳಿ? ವಾಯ್ಸ್ ಕೇಳಿಸ್ತಾ ಇಲ್ಲ? ಹಲೋ
ಸರ್ ವಾಯ್ಸ್ ಕೇಳಿಸ್ತಿಲ್ಲ ಸರ್.
ಓಕೆ. Now it is audible. Now it is audible. Anyone? Hello? Anyone?
ಎಸ್ ಸರ್.
ಆಡಿಬಲ್ಲ ಕೇಳಿಸ್ತಾ ಇದ್ದೀನಪ್ಪ.
ಕೇಳಿಸ್ತಿದೆ ಸರ್.
ಇಟ್ಸ್ ವಿಸಿಬಲ್ ಆಲ್ಸೋ.
ಎಸ್ ಸರ್. ಎಸ್ ಸರ್, ಇಟ್ಸ್ ವಿಸಿಬಲ್.
No problem. Okay.
No sir.
I'll read the problem once again. Air enters the compressor of an ideal air standard Brayton cycle at 100 kPa, 300 Kelvin with a volumetric flow rate is 6 meter cube per second. Compressor pressure ratio is 10. The turbine inlet temperature is 4500 Kelvin. Determine the thermal efficiency, work ratio, and power development. I said the earlier problem also the same thing. You read the statement of the problem twice and then you go on writing the given data with notations. And also one more important thing I said, for any cycle PV diagram and TS diagram carries 2 marks. Okay, if you write the PV diagram and TS diagram very clearly, then you will be awarded 2 marks in the examination and in the test also. Given data, Brayton cycle, he has given the Brayton cycle, a standard Brayton cycle. P1 inlet pressure is 100 kPa, 100 into 10 to the power of 3 kilo means 10 to the power of 3 Newton per meter square. T1 is 300 Kelvin, directly he has given in Kelvin, no need to change. V1 is 6 meter cube per second. RP, the pressure ratio, P2 by P1. Okay, 1 to 2 is the pressure ratio you will get. In the Otto cycle, diesel dual cycle, it is a compression ratio, but here in the Brayton cycle, it is a pressure ratio. P2 by P1 is equal to P3 by P4, P3 by P4. P3 is higher one, P4 is lower one, P2 is higher one, P1 is lower one. So that P2 by P1 is equal to P3 by P4 is equal to 10. Determine thermal efficiency, neta, work ratio, and power developed. For this, the isentropic process 1 to 2, T2 by T1 is equal to P2 by P1 raised to the power of gamma minus 1 by gamma. T2 is equal to, you will get the T2. Compression work, compressor work. Compression takes place between 1 to 2 compression. Okay, so that compressor work is WC CP. Why it is CP? 1 to 2 constant pressure. 1 to 2 it is a constant pressure. Okay, CP T2 minus T1. 1.005 it is a standard value. He has not given, you have to assume into 10 to the power of 3 because you are substituting in Newton per meter square. That's why you are getting joule per kg. Otherwise it becomes a kilojoule. Okay, T2 just now you are calculated and T1 minus T1. Process 3 to 4 reversible adiabatic process. 3 to 4 is a reversible adiabatic process. Okay, P4 by P3 is equal to T4 by T3 is equal to P4 by P3. raised to the power of gamma minus 1 by gamma. Gamma is the value of the ratio of specific heats. It is 1.4. 1 by gamma minus 1 by gamma R. T4 is equal to 776.95 Kelvin. Turbine work you can calculate. Turbine work, where the turbine work comes, you see here. Turbine work. Work output is the turbine work. Work input is the compressor work. Turbine work occurs in 3 to 4. That's why turbine work is equal to Cp. T3 minus T4, it's 1.005 into 10 to the power of 3 is kilojoules is converted into joules. 1500 minus 775.95. 1500 is given. 775 you are calculated. Turbine work is 726.10 to the power of 3 joule per kg. Net work done is compressor work minus turbine work. Compressor work, turbine work you are calculated compressor work, because turbine work always more than the compressor work. Otherwise, the whole system will fails. Work net work output is 446.08 into 10 to the power of 3 joules per kg. Heat supplied is Q2 to 1. Heat supplied is 2 to 3. Okay. It is constant pressure. Q is equal to mCp T3 minus T2. Heat supplied T3 minus T2. Okay. 1.005 10 to the power of 3 into T3 is given 1500 minus 579. You'll get the 920.81 into 10 to the power of 3 joule per kg. Otherwise, kilojoules per kg. Thermal efficiency is net work done divided by heat supply. Net work done is 446. Heat supply you are calculated, you will get the 48.44. Work ratio is nothing but the net work done divided by turbine work. Net work done divided by net work done is turbine work minus compressor work. Net work output, it is 446.08, just now we are calculated. And also the turbine work, you have to take the turbine work here also. You'll get the work ratio. Mass flow rate is M, PV is equal to MRT. From that equation, P1V1 is equal to MRT1. P1 is given 100 into 10 to the power of 3 kilo into V1 is 6 meter cube per second. R is 0.287 into 10 to the power of 3. T1 is given 3300 Kelvin. You'll get the mass flow rate is 6.97 kg per second. Power developed is nothing but the P into mass developed into net work done. Mass is 6.67 into 446.08 into 10 to the power of 3. You'll get the 3109.18 into 10 to the power of 3 joule per second. Joule per second is nothing but the watt. Okay. Otherwise, kilowatt. Whole thing. 3109.18 kilowatt. Next, according to the Brayton cycle, actual cycle is varies from the ideal one. Previously, what we are calculated is the ideal one. It's the actual case. Here enters a compressor of an open cycle constant pressure. Open cycle constant pressure gas turbine. Gas turbine means Brayton cycle equation. At a pressure of 1 bar, inlet pressure, inlet temperature 20 degree, 20 plus 273, 293. It is 1 bar, 1 into 10 to the power of 5 Newton per meter square. Pressure of air compressor compression is after air compression is 4 bar. Okay. After that 4 into 10 to the power of 5 Newton per meter square. Here. Isentropic efficiency of the compressor and turbine is 80%, 85%. Isentropic efficiency is given. Like this you have to write dotted line. Okay. The air fuel ratio is 90:1. Calorific value of the fuel is 42,000 kilojoules per kg. If the flow rate of air is 3 kg per second, find the power developed thermal efficiency of the cycle. Given data, Brayton cycle, P1 in bars, it's converted Newton per meter square. T1 is 20 into 20 plus 273, 293. P2 4 into 10 to the power of 5 Newton per meter square. And neta C, neta T is given 0.8 and 0.85. MA by MF is 90. CV is 42,000 10 to the power of 3 joules per kg. Mass is 3 kg per second. Assumption you have to assume, because he has not given CP value or CV value, gamma value. You have to assume for the air, standard air, it is a standard values. So that you have to assume. To determine the power developed thermal efficiency. For that solution, the process 1 to 2, the isentropic and reversible adiabatic compression process T2 by T1 from that equation you will get that T2 is equal to 435.39 Kelvin. Actual temperature at the compressor outlet T2 is equal to, we know that the compressor efficiency is compressor, it is always compressor T2 minus T1 divided by T2 dash minus T1. T2 dash, you see here, T2 dash, okay, T2 dash by T1. Instead of this, you can take the enthalpy also. If given in the enthalpy wise, you have to take the same formula with H notation. Okay, enthalpy. T2 is 470.99 Kelvin. Compressor work is MCP T2 minus T1. It is 1.005 standard value. Assume into 10 to the power of 3 is convert the kilojoules per kg into joules per kg into the T2 is 47.99 minus 293. You'll get the 178 into 10 to the power of 3 joules per kg. Turbine inlet temperature T3, you know that heat supplied of the fuel is equal to heat of combustion. Heat supplied M into CV is equal to MF plus MA into CP T3 minus T2 dash. CV is equal to 1 plus M dash by M dash F CP into T3 minus T2 dash. By substituting all the values, you will get the T3 is equal to 390.23 Kelvin. Process 3 to 4 is isentropic or reversible adiabatic expansion. T4 by T3, from that equation, you will get that T4 is equal to 626.10 Kelvin. Actual work, turbine work, N theta is equal to, NT is equal to T3 minus T4 dash divided by T3 minus T4. 0.85, 930 minus T4 dash 930 minus 626. We will get this 671.64 Kelvin. Turbine work CP value into T3 minus T4. Net work done is the WT minus WC, compressor and the turbine difference. Okay, substituting all the values, you will get the net work done is 81.81 into 10 to the power of 3 joules per kg. Heat supplied is Q2 to 3 MCP CP T3 minus T2 dash 1.005 into 10 to the power of 3 into 930 minus 470. You'll get the Q supply 461.54 into 10 to the power of 3 joule per kg. Thermal efficiency is W net minus Q supply is equal to 81 divided by 461.54. You'll get the 17.54%. Overdeveloped is P. P is equal to M dash W net. You'll get, substitute this. You'll get. In the third turbine, the third problem, a simple gas turbine unit, the isentropic discharge temperature of the air flowing out of the compressor is 195 degrees Celsius, while the discharge temperature is 240 degrees Celsius. Air conditions at the compressor at inlet are 1 bar and 70 degrees Celsius. If the air fuel ratio is 75 and the net power output from the inlet of the inlet is 640 kilowatt, compute isentropic efficiency of compressor and turbine. Overall efficiency is a cycle. Calorific value of the fuel is 461, 46,101 kilojoules per kg, and the net consumes and the unit consumes 312 kg per hour of the fuel. Assume gases CP value is 1.09. Here you must be very careful. For gas he has given particularly, so that you have to take this. Don't assume, you have to take this. Gamma 1.32, CP value 1.005, gamma is 1.4. For air you have to take the burnt gases are PLS, CP and CV gamma values. For that Brayton cycle T2 dash you convert this and then all the remaining given data. This TS diagram is more than sufficient for this compressor efficiency and turbine efficiency individually as given. For gases its CP value is 1.009 into 10 to the power of 3 and gamma value is 1.32. For air it is CP value is 1.005 it is converted into meters 1.005 into 10 to the power 3, and gamma value of the air is 1.4. Like that, gamma value of the gas is 1.32. Pressure ratio RP is equal to P2 by P1. P2 by T1 is into raised to the power of gamma divided by gamma minus 1. We substitute all things. RP is 5.32. Compressor efficiency is the T2 minus T1, T2 dash minus T1. We'll get the 79.85. Compressor work is MA CPM into T2 dash minus T1. M is 6.525 into 1.005 into 10 to the power 3 into 513 minus 290. W compressor is equal to 1469.35 joules. Joules per second or watts. Turbine inlet, you can calculate the turbine inlet from that T3, and then turbine work is actual compressor and turbine. After that, actual turbine work outlet temperature is T4 is 776.53 Kelvin. For process 3 to 4 isentropic or reversible adiabatic expansion, T4 by T1 is equal to P4 by P1 raised to the power of gamma minus 1 by gamma. 1 minus RP gamma minus 1 by gamma is equal to T4 is equal to T3 by RP to the power of gamma minus 1 by gamma. You substitute all things, you get the T4 is equal to 712.65 Kelvin. Turbine efficiency is also T4 minus T3 minus T4 dash divided by T3 minus T2. If you substitute all the things, you'll get T3 and T4 dash and T3 T4. You'll get all the things. You'll get the efficiency of the turbine is 0.82. Heat supplied is Q supplied M dash CV into is equal to 1.00 is equal to 1.087 into 10 to the power of 10 into 461.10 into 10 to the power of 3. Q supply is 4011.57 into 10 to the power of 3 joules per second. Cycle efficiency is W net by heat supply that you are calculating. Here, by looking into these problems, you can observe all the problems are similar. Only the thing is you must know the derivation properly. Otherwise, it's very difficult to make any problem. Here, one more problem is there. You can read this statement of the problem. Air is drawn in a gas turbine 18 degree. Initial temperature T1 18 and the pressure is 1 bar. Leaves the compressor as 5 bar. P2 is 5 bar. Data observed are temperature and gases entering the turbine 678 degrees Celsius. Previous loss in the combustion chamber is 0.1 bar. Efficiency of the compressor is 85%. Efficiency of the combustion is equal to 85%. Efficiency of the turbine is 80%. Gamma is 1.4, Cp value is 1.028, and gamma is 1.3 for gases. Determine the quality of air of a plant develops 1065 kilowatt. Heat supplied per kg of air is calculate thermal efficiency of the cycle. This problem also same. The here efficiency of compressor and the efficiency of the turbine is given individually. Then yes, given the Brayton cycle with losses. Okay, that you must consider. Okay. Same. Only thing is the pressure loss, he has taken the pressure loss here, extra one. That also you can count. There are methods of improving the work output of the Brayton cycle. Some of the methods used for the improving the work output, those are regeneration. Utilization of heat present in the exhaust gases to the preheat the air supplied to the combustion chamber. Means the exhaust gases is recirculated in the combustion chamber so that the inlet air can be heated up. That is called as regeneration. Regeneration is nothing but the waste heat recovery system. Waste heat is which is going to the atmosphere, it is trapped and then it is utilized for the other purpose in the engine cylinder so that efficiency can be increased. Intercooling of air compressed in the first stage of the initial temperature before it's sent to the second stage compressor. The rules in reducing the work output to the multi-storage compressor results in the reducing the work input to the multi-stage compressor. Reheating, the air expands the first stage of the maximum cycle temperature before it's sent to the second stage of the turbine. Results in increasing the work output at the multi-stage turbine. All these things, nothing but all three methods are regeneration, reheating, and the intercooling are the methods of improving the thermal efficiency. In that, regeneration is nothing but the waste heat recovery system. Waste heat which is going to the atmosphere that is trapped and it is used for the increasing the efficiency. Thank you.